Hello dear students. Today let us learn what is an isochoric motion of a continuum and the equivalent statements in an isochoric motion. Of course in fluid mechanics. Let us see what is an isochoric motion. Before that, let us see some of the uh, elementary definitions or some relations. Okay, let us take a moving continuum. So whenever we have a moving continuum, we have dV naught, right, which is nothing but the volume element in the initial configuration, and dV is the volume element in the current configuration. V naught in the initial and V in the current configuration. Okay, so we have taken small elements dV naught and dV. Fine, and we know that they are related through the Jacobian. dV is equal to J dV naught. Let us call it as equation 1. We'll take the material time rate of change on both sides. So d by dt of dV equal to d by dt of J dV naught. And J dV naught is function of product of two functions, J into dV naught. So we'll J as it is, differential of dV naught plus dV naught as it is, differential of J, right, using product rule. And we know that V naught is constant or fixed. So therefore we have this dV naught by dt is 0, or dV naught, small dV naught is also constant. So therefore d by dt of the dV naught is going to 0. This first term will vanish. Only the second term will remain. So dJ by dt dV naught. And by Euler's formula, what is the dJ by dt? dJ by dt is nothing but J into dV, dV naught as it is, right? And this J into dV naught together is nothing but dV, using relation 1. So we get d by dt of dV is equal to divergence of the velocity t into dV. Fine. So what is divergence V from this relation? Divergence V is nothing but 1 by dV d by dt of dV. So let us call it as equation 2. So what is divergence V representing actually? It represents the material rate of change of volume per the unit volume of the material element. See, the material rate of change of dV divided by dV, right? So material time rate of change of volume per unit volume of the material element as it moves with the velocity v, small vector v. So that is our equation 2. So divergence v is equal to this whole thing. Okay. Now let us see what is an isochoric motion. A motion is said to be isochoric. A motion is said to be, of course, of a continuum, is said to be isochoric if divergence of the velocity is constant during the motion. During that motion, if the divergence of the velocity is constant, then that motion is said to be isochoric. In other words, by using equation 2, what is our equation 2? Divergence V is equivalent to this, right? So in other words, a motion is said to be isochoric. So divergence V is constant. That means what? We have that dV is constant. dV is 0. Divergence V is constant, no. So we get divergence V is constant. So we get, using equation 2, volume is preserved during the motion. Iso means same, choric means volume. Same volume. A motion is said to be isochoric if the volume is same during the motion or volume is preserved during the motion. Okay. Now let us prove for an isochoric motion 3 things are equivalent. What What are they? Let us see. Now from equation 2, what is our equation 2? It is seen that dv equal to constant, dv equal to constant, if and only if divergence v is 0. If and only if divergence v is 0 from equation 2. Just watch equation 2. Equation 2 says, yeah, this is our equation 2. Equation 2 says divergence v, if this is 0, then we get what? We get, capital dv by dt equal to 0. That means this dv equal to constant. dv equal to constant. Fine, that's what is written here. So from equation 2, it is seen that dv equal to constant if and only if divergence v is 0. Okay, yes. Now let us take the Euler's formula. So dj by dt is equal to j into divergence v. Divergence v, now put divergence v equal to 0 here. So what are we going to get? So this part is 0, the RHS is 0. So we get dj by dt equal to 0. That means what? J is constant during the motion. J is constant during the motion. Fine. All these things are equivalent. dv equal to constant, or divergence v equal to 0, or J is constant during the motion. Fine. Now, J is constant during the motion. Okay. What is J? J is nothing but determinant of dou xi, right, by dou xj naught, I equal to 1, 2, 3, j equal to 1, 2, 3. Fine. Differentiation of the current coordinates with respect to the material coordinates. So dou x1 by dou x1 naught, x2 naught, x3 naught. And we have, dou x2 by x1 naught, dou x2 by x2 naught, x3 naught. And then we have x3 here. x3, x3, x3. With respect to x1 naught, x2 naught, x3 naught. That's our J. Okay. Now, when t equal to 0, when t equal to 0, we know that xi equal to xi naught. Correct? So, when t equal to 0, put xi equal to xi naught. So, this x1 will become x1 naught, x1 naught, x1 naught. And x1 naught with respect to x1 naught. Differentiation of x1 naught with respect to x1 naught is 1. Fine. Then, dou x1 naught with respect to dou x2 naught. So, it is 0. x1 naught with respect to x3 naught is 0. Similarly, dou x2 by dou x2 naught by dou x1 naught is 0. Okay. Then dou x2 naught with respect to dou x2 naught is 1. And dou x2 naught with respect to x3 naught is 0. Similarly, the third row. So expand this determinant. Determinant value is 1. Fine. So j equal to 1. J equal to 1, which is in the beginning when t equal to 0, before the the beginning of the motion of the continuum. And what is the J? J is constant during the motion. J is constant during the motion. To begin with what? What is our J? To begin with, J is 1. Begin with means what? When t equal to 0, what is J? J is 1. J is 1. And J is constant during the motion. J is constant during the motion. Now applying these two, what is happening now? So applying these two, we get J t equal to 0, J is 1, and J is constant during the motion. Apply these two together. So we are going to get what? We get, it implies that J is 1 throughout the motion. J is 1 throughout the motion. Okay. So therefore, divergence V equal to 0 if and only if J equal to 1. Or the motion is isochoric. Divergence V equal to 0 means what? The motion is isochoric if and only if J equal to 1. Thus, we have proved the following statements for an isochoric motion. What are the statements? The statements are this. dV equal to constant. Capital V here denotes volume. dV is the volume element is constant, or divergence of the velocity equal to 0, or J equal to 1. All the three statements are equivalent for an isochoric motion. So we proved very, very important theorem. Now let us see the next statements. It says this: if the above condition holds good for every motion of a continuum, then that continuum will be called incompressible continuum. In other words, a continuum is an incompressible continuum if and only if every motion of that continuum is isochoric, volume is preserved. And incompressible means liquids. Incompressible continuum is nothing but liquids. So for liquid, volume is preserved, volume is constant. So a continuum is said to be an incompressible continuum if and only if every motion of that continuum is isochoric. Okay, now let us see what is a stream tube. The streamlines drawn from each point of a closed curve C in the current configuration, where in the current configuration is called stream tube. The strength of this stream tube is nothing but surface integral S V dot N ds. That is the strength of the stream tube. Strength of the stream tube is nothing but the flux of velocity across the surface S enclosing the volume V. Enclosing the volume capital V. Okay, where small v vector is the velocity, n is the unit outward normal. N is unit outward normal, very, very important. It is outward normal. And S is the cross section of the tube. Cross section of the tube. Okay, yes, that's about the stream tube. So definition of stream tube. Now, this is the stream tube. So we have, you can see we have a closed curve. This is the closed curve. Okay, closed curve. S1 is a surface. Okay, covering that closed curve C. And these arrows indicate the direction of velocity. The arrows indicate the direction of velocity. These arrows denote the direction of the velocity of the continuum. And this is another surface. Okay, this is another surface. This is S2. Fine. So this stream tube will have three surfaces. One is S1 at the end, one end. The other end we have S2, and in between, I mean the curved surface, that is this surface, is another surface. You can call that surface as S or S dash. Okay, it will have three surfaces. Okay, and what is the normal of this S1? S1 normal is N, outward normal. And for S2, it is, is okay, yes. Now we have to prove a theorem. The theorem is this: the strength of a stream tube, strength of the stream tube is constant for an isochoric motion. Isochoric motion. The strength of a stream tube is constant for an isochoric motion. Okay, let us take a stream tube in an isochoric motion of a continuum. Okay, let us take that continuum. There is one more diagram here. Yes. So we have, of course, three surfaces, as we have said. We have S1, we have S2, and that curved surface S dash. And that surface, that curve C is closed. And this is in the current configuration at time t greater than 0. Okay, yes. So now we have, by the Gauss divergence theorem. What is Gauss divergence theorem? We have this theorem, very important theorem. It says that volume integral divergence V dV is equal to surface integral V dot n ds. This is the Gauss divergence theorem. Conversion of volume integral to surface integral, right? Okay. What is S here? S is the total surface. Now we are applying this for the full volume of this stream tube, which is having the surface S, and S has three surfaces. One is S1, the other one is S2, and the other one is S dash. S dash is the curved surface, curved part of the stream tube. So applying this, now our S will have three surfaces. So, comma, integral volume integral divergence V dV is equal to, so S will have 3. So S1 plus S2 plus S dash, same integrand V dot n ds as it is. Now there are three surfaces now. We'll split the integrals. So first integral over S1, integral over S2, and integral over S dash. Integral over S dash. Okay. Now this V dot n on S dash, very important, on S dash, V dot n. What is V? V is direction of the continuum, that is this direction. So this is V direction, and n direction, if I take any small surface ds, n direction will be a normal direction, right? That is n. So if for any surface ds here, for any surface ds there, if I take any surface, small surface on that curved surface ds, okay, V and n will be perpendicular to each other. So V means vector, velocity vector. So V dot n equal to 0 on that curved surface S. So therefore, this integral, that is over S dash, will become equal to 0. So this integral vanishes. Okay, we have only two integrals now. We have only two integrals. So what is our LHS? LHS is volume integral divergence V dV equal to. Now look at S1. So what is S1? S1 is this is our S1. The starting that is this. This is our S1. Fine, to start with. Suppose we move along with the direction of the continuum. Suppose we move along with the direction of the continuum like this. Suppose we move along with the direction of the continuum. So what is n? So n is in the opposite direction for S1. For S1, n is in the opposite direction. For S2, it is in the same direction. Same direction as the velocity. Okay, so as we move along with the direction of the velocity of the continuum, fine, this n is opposite to the direction of the continuum, this n. So whenever I deal with S1, we are going to take that as negative, just to denote that its direction is opposite to the direction where we are going, right? We are going along with the direction of the continuum. And for S2, it is in the same direction. See, this is n direction, and this is our velocity direction. Velocity direction, both are same. So it is plus for whenever we take with S2, and whenever we take with S1, it is negative. Fine. Okay. So that is why the sign negative here. So minus uh, surface integral S1 V dot n and plus S2 V dot n. Fine. And since the motion is isochoric, divergence V is 0. So apply this. We get this part will go now. So this is 0 here. This is 0. And shifting one of the integrals the other side. Whichever is negative here will shift to the other side. So we get the surface integral S1 V dot n is equal to surface integral V dot n ds on the surface S2 and S1. That means what? That means the flux of the velocity over the surface S1 is equal to the flux of the velocity across the surface S2. So flux of velocity means the strength of the stream tube at S1 is equal to strength of the stream tube at S2. So whatever is in the beginning, it is same in the end. So therefore, the strength of the stream tube is constant for an isochoric motion. Okay. Now, let us take a vortex tube. Next theorem is to prove that the strength of the vortex tube is constant for all motions. Very, very important for any motion. For any motion of the continuum, the strength of the vortex tube is constant. To prove it is constant. Okay, what is vortex tube? The vortex lines drawn from each point of a closed curve C, where in the current configuration is called vortex tube. And the strength of the vortex tube is denoted by surface integral S, omega here, or W. Okay, you can denote W also, no problem. Okay, V dot N ds, where W is the vorticity. W dot N ds, where W is the vorticity. What is N? N is the outward unit normal and S is the cross section of the tube. Fine. So by Gauss divergence theorem, we have volume integral of divergence of this. We can take omega. Omega dV is equal to surface integral of that omega dot N ds. That's by Gauss divergence theorem. And we know that what is the total surface now? This is the vortex tube. That you look at the diagram of same diagram for the vortex tube also, right? We can have that vortex tube having three surfaces, S1, S2 and S dash. S dash is that curved surface. Fine. And the arrows, here denote the direction of the velocity. The arrows here denote the direction of the vorticity. Direction of the vorticity omega or W. So surface S is nothing but S1, S2, S3. So we have S1 plus S2 plus S3 dash, where S1 and S2 are the cross sections of the vortex tube S dash. And S dash is the curved, here, comma, S dash is the curved surface of the vortex tube. Okay. Why on the curved surface it is equal to 0? Because we have on the curved surface that W is perpendicular to N. Vorticity is perpendicular to N on the curved surface. So this third term will go off. Okay. And we know that divergence of W. And what is W? W is curl of the velocity. This W, vorticity, is nothing but curl of the velocity. So use that. And we know that curl of divergence is 0. Is 0. So using that in the above relation, so we have this is also 0. So this 0 equal to, we have only two terms over S1 and S2 equal to 0. Fine. Now, negative sign we have taken for S1. For the reason that we are going along with in the direction of the vorticity W, and on S1, right, N is opposite to the direction of the W, so it is minus. And for the next one, for S2 it is plus. S2 it is plus, equal to 0. Now, whichever is the minus sign, chain, we will go to the other side. So we have the integral of w dot n over S1 is equal to the same thing over integral over S2. That means what? The strength of the vertex tube at S1 is equal to strength of the vertex tube at S2. That implies the strength of the vertex tube is constant for any motion of the continuum. For any motion of the continuum. For all motions. Whereas strength of a stream tube is constant only for isochoric motion. For isochoric motion, we get divergence of velocity equal to 0. That is fine. There is a condition for the strength of the stream tube to be equal to 0. Whereas strength of a vertex tube is always constant for any motion of the continuum. Yeah, thank you. We'll stop now. We'll continue later. Thank you.